My name is Isaac, and I'm a PhD student at the University of Laval, working under the supervision of Professor Carl Guillemette and Professor Doug Tinkerman. And today, I'm going to share some results of my ongoing PhD project, mainly focused on the metamorphic and structural records of the North Pontiac subprovince, and how we can use these data sets to decipher its Newarkian crustal architecture and thermal state. So, debates regarding the geodynamic evolution of the Superior Kraton have been a long-standing issue, and yet it's not well understood. While some studies considering that plate tectonic process drove the Newarkian assembly of the Superior, other studies show that mantle overturn events caused the disaggregation of the Superior, followed by a fast reaccretion of rainbow continents. This dichotomy plays an important role in how we see the tectonic evolution of the metasedimentary belt, which the Pontiac is part of it, and if we should considering them as an accretionary prisms in a plate tectonic scenario, or extensional basins in a stagnant lead tectonic scenarios. And one of the best tools we have in hand to decipher the crustal architecture and the thermal state of these metasedimentary belts is the metamorphic gradient. It can be divided in average thermal gradient and metamorphic gradients. The average thermal gradient simply portrays the relationship between temperature and depth at the choosing point during metamorphism. And it can be used as a discriminatory tool to thermal regimes and tectonic settings, as you can see here in this figure. On the other hand, metamorphic gradients record spatial patterns and the metamorphic variation along a horizontal plane, and the pressure and temperature paths experienced by rocks along these gradients. It can be used to decipher tectonic disturbance with direct implications on the magnitude, shape, and PT trajectories. So we decided to use this approach in the Pontiac subprovince that's separated by the Cadillac-Larder Lake Fault from the Abitibi, which is a world-renowned gold district. And we know that the basement rocks mainly consist of a TTG gneiss suite that it's exposed in the west, in the south part of the area. There is an important plutonism in the area represented by a sanuctoid suite and S-type granites placed across the central part of the area in the southernmost part. Antoine will talk a little bit about the intrusive record after this talk. And in the north part, it's mainly represented by turbiditic sequence with wax, mudstones, with concordant komatitic and basaltic flows. We know that the maximum depositional age is around 2682 million years, and that the metasediments display of Barovian-like sequence from biotite to the silimanite zone, even to partial melting. And there's also have been mentions of Andaluzite and cordierite assemblies, but nothing is clearly documented yet. We also know that the prograde metamorphic age is around 2657 million years, based on Lutetian, Hafnium, garnet dating on starolite zone rocks from the Valdor region. And we decided to use this area here because it preserves a completely Barovian-like sequence within relatively small geographic area. Previous studies that focus on detrital, seismic, volcanic, and magmatic records have led to contrasting tectonic models in which the Pontiac was formed and evolved as an exotic terrain, collided with the Abitibi, but new studies haven't shown that both the Pontiac and the Abitibi share similar detrital-zircon provenance, so nowadays this model is outdated. There's an accretionary prism model where the Pontiac was deposited next to the Abitibi subprovince in a subduction setting, and we have also a reverse rift model where mantle overturn events favor the opening of an extensional basin, followed by a fast reaccretion of rainbow continents. And more recently, we have a new model, a plume-related rift basin model, where the Pontiac was developed as an extensional basin within the older Abitibi volcanic arc, followed by a period of short-lived subduction. Besides the controversial tectonic models, there is a conflict point of view on the structural geology as well. Even though previous studies report a north to south Barrovian metamorphic field gradient and southeast virgin fold and thrust structures, it remains unclear whether the metamorphic field gradient continues across the sequence or disrupted by a thrust fault separating two nappes with different metamorphic histories and different tectonic fabrics. So before we deal with the tectonic models, we should better understand the regional context of the North Pontiac subprovince. So what's missing for us is to test these two nappe models by combining structural investigations with quantitative metamorphic studies. So how can you do that? We start by selecting metapelitic rocks in a well-known structural context that have pressure and temperature sensitive mineral assemblies. So then we can apply a petrochronology approach by using microstructural, microtextural relationship, phase equilibrium modeling, also using UPB monazite and zircon dating, and lutetium hafnium garnet dating. So in the end, we can reconstruct the pressure, the temperature, the time, and deformation paths. And most important, we can then study the metamorphic gradients across the Barrovian-like sequence. So our first step was to remap the metamorphic isogrades and metamorphic zones across the sequence, trying to identify index metamorphic minerals. So 4 metamorphic isogrades were defined with increase of grade from north to south, passing through the garnet zone, the starolite zone, the kyanite zone, and the sillimanite zone. Even though we didn't find kyanite zone samples, some works have reported the presence of kyanite and with garnet and starolite. That's the reason we trace here an isograde here. As described in previous studies, 2 deformation phases were recognized. During D1, a subvertical to vertical northeastern cleavage is developed parallel to the bedding planes according to the position of F1 folds. D2 was responsible for overprinting D1 related structures, and they're producing a vertical east-west trend crenulation cleavage that's axial planar to the regional F2 folds. As you can see here, at the map scale, the regional F2 folds, and at intersection scales where we have here transposed quartz veins and the relationship between the F1 and the F2. So with a better knowledge of the deformation phase, we start to looking for clues in thin sections, trying to link the sequence of deformation phase to the development of porphyroblast growth across the metamorphic zones. So here at the lower grade in the biotite zone, we can see that the S1 mainly occur as microlintons separated by cleavage domains associated with the S2. The S2 progressively evolves from dark seams to the north, as I show at the lower grade, to a complete leptoblastic texture towards the south, where we can see only some S1 relicts, as you can see here. Also, as chromium is an immobile element during prograde metamorphism, we use some chromium garnet maps to support our petrographic observations and to help us to establish the relative time of porphyroblast growth and fabric development. So here what we can see is that we have a garnet that grew late to pos S2 with almost to see the same orientation, slightly rotates through, rotate when you compare with the matrix. At the starolite zone, we cannot see anymore the S1 in the matrix, only preserved as quartz inclusions in pre to CS2 starolite porphyroblasts. Garnets from the starolite zone usually grew and pos S2, as you can see here, almost the same orientation observed with the chromium map is the same orientation we see in the matrix. We can see in the matrix. Unlike the other zones, the sillimanite zone is a little bit tricky because we couldn't see the relationship between the chromium maps and the fabric development. But we can see here that we interpret 2 compositions. A first one here in the core that we interpret the groove at subsolidus conditions, and at the rims that we interpret as a pos S2 garnet rim. Another thing is we observe here that both staurolite and garnet rims are commonly seen observed to be replaced by cordierite, which may be characteristic of isothermal decompression. Overall, the peak metamorphic assemblies were developed after the onset of D1 continuously and after D2. So to test the homogeneity of the protoliths, we obtain whole rock compositions from different samples from different metamorphic zones, and that are plotted here in the FM diagram. The FM diagram is just three-component triangular graph that represents the variation of mineral assemblies as a function of the rock type. So what we can observe here is that there is no grade-related trend here when you compare the metamorphic zones, meaning that the mineral assemblies are mainly controlled by the metamorphic grade rather than raw rock compositions. So from that, we select 5 representative samples that we use for the phase equilibrium modeling. So here are the different steps we took to retrieve the peak PT conditions from the metamorphic rocks. So first we use whole rock geochemistry data, and then we choose the compositional system we want to model these rocks. So in the end, we can calculate the topology of isochemical PT phase diagrams. We also carefully describe the textural relationship between the minerals and estimate the model proportions of the main phase by using micro-XRF maps. Finally, we obtain mineral compositions through microprobe analysis. Indeed, the phase equilibrium modeling is a powerful tool, but it's not a straightforward one. So even though it seems intuitive to use whole rock compositions from the library right away, we still need to apply some bulk corrections. And what we did was we fractionate sulfides by mass balance calculations to account for the extra iron contents available in the modeling system. And from that, we use the mineral proportions and the probe compositions of solid solutions. We also subtract a small amount of calcium to account for apatite presence. And we did that because this phase, sulfides and apatite, we could not reproduce during the phase equilibrium modeling. So in the end, we have here, we subtract a certain amount of iron and calcium for the original bulk, and then we created a model-ready bulk to use with the phase equilibrium modeling. So after that, we calculated here the topology of the PT diagrams. And the first thing to do, we need to check if we're able to reproduce the equilibrium mineral assemblage we observe in thin sections. If the answer is yes, we can then try to reproduce the model proportions of the main phase and the mineral compositions like grossular contents and garnet and nanotite contents and plagioclase. And since this data which gave us a peak PT conditions of 5.6 kilobars and 600 Celsius. Since garnet preserves a prograde growth zoning and calcium has a very slow diffusion rate, we use the grossular contents from garnet from core to ring as a proxy to trace a prograde PT path segment here, as you can observe here. This was the approach to use for all the metamorphic zones and all the PT phase diagrams we calculated. So once we link petrographic observations, structural data, and most important, the peak PT conditions, we are able to distinguish 3 types of PTT paths. A load heating path for garnet zone rocks with peak conditions of 8 kilobars and 505 Celsius, an isobaric heating path for the staurolite zone rocks with peak conditions of 6 kilobars and 610 Celsius, and for the silimanite zone, we see a decompression heating path with peak conditions of 6 kilobars and 710 Celsius. As you can see here, both the staurolite and the silimanite shows moderate thermal gradients, and the garnet zones low thermal gradients. Now let's add time to the equation to see to the PTT path, so we can see how putting the time in the PTT path would show some extra information. So here, we use garnet because garnet grows throughout the increase of PT conditions, and its age can be used to can be used to estimate the timing of prograde metamorphism. So here we obtain ages for all the metamorphic zones, from the garnet, the starolite zone, and the silimanite zone, which is pretty similar for previously published ages around 2657 million years. Also, here we have some representative Lutetian maps where we can see an oscillatory zoning in a well-preserved growth zone with most Lutetian confining their cores, here, so you can see here, meaning that maybe limited internal diffusion hasn't disturbed the system. So based on that, we interpret that this age as the prograde metamorphic ages. We also date monazite and zircon as a second order control for the timing of metamorphism. And for the silimanite zones, monazite yields an age of 2667 million years, which represents a 10 million years time span, if compared with the garnet zone, with the garnet ages. And zircon records 2647 million years. Unfortunately, we couldn't obtain new ages for the other metamorphic zones because of the lack of monazite and zircon in the other zones. So our results for petrochronology point toward the short-lived residence of these rocks at middle crustal conditions and the coexistence of diverse PTT paths along two contrasting dam gradients. While subsolids monazite and garnet date at 2667 million years and 2657 million years, record the constrain the time of prograde metamorphism, suprasolid zircon overgrowth recorded the time of high temperature cooling in all interpretations. So as we start for the assumption that we're dealing with a Barrovian-like sequence, we compare our data with a classic examples of continuous and inverted Barrovian sequence developed in the typical of collision zones and their predictions for the PTT paths, as you can see here. And when you see in both cases, for a continuous and inverted sequence, pressure and temperature increase while average thermogrades decrease from low-grade rocks to high-grade rocks. But when you look to the Pontiac here, what you can see is that pressure decreases towards the high-grade metamorphic rocks, while the average thermograded increase towards the high-grade rocks too. And also, different for the both case, for typical continuous inverted sequence, we have the coexistence of diverse PTT paths that's not typical for the same set of rocks developed that underwent Barrovian metamorphism. Another thing is, when you compare the average thermogradients for continuous inverted Barrovian sequence, we would expect just a trend from low-grade to high-grade rocks, as you can see here. But again, when you look to the Pontiac, you see two contrasting thermal gradients. So it's not compatible with collision zones. So we're going back to the questions, two naps or one coherent structural block. Indeed, our quantitative metamorphic data is consistent with the coexistence of diverse PTT paths along two contrasted thermal gradients. But, however, you wouldn't expect this could be associated with the evolution of a nap stack, but we would expect to develop two naps at the same time and in the same tectonic setting. And also having shown that we have a structural continuity from north to south. And because of that, we rule out the hypothesis of two naps, and we believe that the Pontiac was developed in one coherent structural block. Going back to the Pontiac tectonic models, even though the accretionary prism explains pretty well the turbiditic nature of the Pontiac sourced by the Abitibi, it doesn't reconcile the syndepositional volcanism and the syndepositional sanuctoid magmatism in the area. And for us, most important, it doesn't reconcile the two contrasting thermal gradients developing in one in a subduction setting. So because of that, we rule out the accretionary prism model. Now we have like two models left, a reverse rifting basin and a plume-related rifting basin. And both models has predictions, good predictions for the sedimentary and the metamorphic and the magmatic record. But it predicts a polymetamorphic history for the Pontiac, what is different for what we got for our data. It predicts first a low pressure and high temperature metamorphism overprinted by a typical Barovian metamorphism. In our data, we don't see this, it's not a good fit for our data. So because of that, we rule out these two models. Alternatively, our model is more consistent with a subduction process, where previous numerical modeling having showed the high heat influx into the shallow crust by polyvoluminous magmas could produce crustal overturning, allowing the coexistence of diverse PTT paths, fast barrier and exhumation rates for what we got in our data, and contrasting thermal gradients. And also, it's important to say this model is based only on the metamorphic record. So we need to tie up some loose ends when dealing with the sedimentary and the magmatic records to create a viable tectonic model for the Pontiac subprovince. Thank you very much for your time.